Hello and welcome to Math 253 here at Cañada College. My name is Lapuz. In this video we will do checkpoint 6.63 from section 6.7 in our OpenStax textbook on Calculus 3. Here they want us to use Stokes' theorem to calculate the line integral, the integral of f dotted with dr over the curve C, where the vector field f is z, x, y, and the curve C is oriented clockwise. It is the boundary of a triangle with vertices 0, 0, 1, 3, 0, negative 2, and 0, 1, 2. So Stokes' theorem will allow us to trade a line integral to the flux of the curl of this vector field over a surface. Now this is a triangular region, and so I'm assuming that our surface will end up being a plane. But let's go ahead and work this out so we can verify that fact. Let's begin by trying to graph these points on your XYZ space. And it looks like I have the point 0, 0, 1 that's just up along the z-axis. I have a 3 in the x, 0, and a negative 2 in the y, so 3 in the x, 0 in the y, and then down 2 units. So this is 3, 0, negative 2. And then I have a 0 in the x, 1 in the y, and up 2 units. I suppose that's a little bit higher over here. So there's a 1 in the x, 1 in the y, 0 in the x, 1 in the y, and 2 in the z. So 0, 1, 2. Kind of hard to see, but that's more or less how it looks like. What might be good here is to try to identify this clockwise orientation. What might be good is to look at this graph directly down on the XY plane. So directly down on the XY plane, we can ignore the z. I mean, we can write it down, but if we just take a look at the first two components of the point, I have a 0, 0 for my first two components. And then 1 is just the z component, which I'm going to ignore in the picture. I'll put it there, but I'll ignore it in the picture, just to get that view from above. And then our next point is 3, 0, negative 2, so the 3, 0 would be along the x-axis, and then negative 2 is the z component, but again we'll set that aside and not worry about it. And finally there's 0, 1, 2, so 0, 1 is this point in the xy plane, but then we'll throw in the 2 here to say, okay, this is just the view from the top, so that we see the x and y axis. Now that we have that, we can kind of better define the orientation, or the idea of the orientation. And if it's going in a clockwise direction, we should be going this way up along the y, and then from the point 0, 1 to 3, 0, and then back to 0, 0. Okay, now imagine that we're doing this directly. If we were to do this direct computation, this is actually not just a line integral, but actually a circulation, because it forms a closed curve. So this is a circulation of the vector field dotted with dr. Now, in doing this, we are going to note that we have 3 pieces of a curve. Let's call this one C1, C2, and C3. And so to do this direct computation, we have to do 3 line integrals, and then we have to add them all up. Now these line integrals are not circulations anymore because the curves themselves by themselves are not closed, but put them together you form a closed curve, and that's how you get the circulation. Okay, but none of that will be important for us, because instead of doing it the way they're asking us, or instead of doing it directly with a line integral, they're asking us to use Stokes' theorem. So Stokes' theorem relates our line integral, our circulation, our closed curve line integral, with, I'm sorry, this is the R, I think we're using R here. We're going to replace the line integral with a flux integral, and we're going to take the curl of f, that be capital S. So what we need to do is we need to define a surface S here in this scenario, and we also have to find the curl of this vector field. Alright, so let's set this direct computation aside and let's do this in pieces. Let's find the curl first. The curl of f will be, let's see, this is our vector field, so imagine we're going to take the cross product of the del operator with this vector field, and we will get with respect to x, the derivative of y with respect to y minus the derivative of x with respect to z, and then the middle term will get a built-in negative sign, the derivative of y with respect to x minus the derivative of z with respect to z, and then the last component is the derivative of y of x with respect to x and the derivative of z with respect to y. So I think this turns out to be a constant vector, which is great. So this vector field is just 1, 1, 1. Okay, now we also need to parameterize the surface. So what is the surface? Again, I think the surface that we end up wanting is a plane that connects, that's coming from these 3 points. So 3 points define a plane in 3D. So let's figure out what that plane looks like. We will figure out this plane by finding finding a couple of vectors. Let's find this vector here and this vector here. Let's call it v1 and v2. v1 vector will be the difference between 3, 0, negative 2, and 0, 0, 1. So that's 3 minus 0, 0 minus 0, and negative 2 minus 1. I believe that's a negative 3. Our second vector on the plane will be the difference between 0, 1, 2, and 0, 0, 1. So that's 0, 1, 1. And then we'll cross that to find our normal vector. So the cross product of this is going to be a, so with respect to x, it's 0 minus negative 3, so that's a positive 3. The middle term will be a negative, and that's a 3 minus 0, so that's negative 3. And then 3 minus 0, so the 3. I think it might be better for us if we consider, just for the sake of computation, let's scale this, because we just want the direction of this. The magnitude is not going to make a difference. So let's use this to be our normal vector. And from here we can get the equation of a plane. So it's going to be the normal, so it's going to be, we need a point and a normal, and our point 0, 0, 1 has more zeros than all the others, so let's use that. And so to find the equation of a plane, I have 1 times x minus 1 times y minus 1 times z is equal to the d, which is a dot product between the point and the normal. So that's 0 times 0 times 1. So I have z is equal to 1 minus x minus negative, so that's a plus y. So that's the plane that I have. Now, to get the parameterization for that plane, we will need to parameterize this. So parameterization will give us an r, and we'll use the graph parameterization so that x is x, y is y, and z is going to be whatever this plane is. So 1 minus x plus y. And then just to skip a few steps over here, we can find Rx separately, Ry separately, and take the cross product. But we know that when we cross the graph parameterization, the first term will be the negative of the derivative of z with respect to x. So that's negative 1. The negative 1 is positive 1. The next is the derivative. It's the derivative of z with respect to y, and that's positive 1, but then it's going to be the negative of that, so it's negative 1. And then the last component is always going to be 1 for our graph parameterization. Okay. If you're unsure of the step, take the derivative with respect to x, take the derivative with respect to y, and then cross them, and you'll get this result. And this shouldn't be a surprise. A plane has a normal vector that's going to be constant, and so we should get the same deal. Now, at this point is usually the point where we want to check the orientation. If we take a look at the orientation here, I see my normal vector is pointing upward. So my normal vector is pointing upward. So imagine your normal vector pointing upward. If you imagine this pointing up, let's say this arrow is coming directly at you, the rotation that we have is going to be going in right-hand rule rotation. And that, if you notice, is the opposite of where we want to go for our curve. So our parameterization here is an orientation reversing parameterization. So ORP, which means we want to have it go the other way. Now, the way we'll deal with that is in the end, there's just going to be a negative sign, so don't forget the negative at the end. Okay, so we'll throw a negative sign there. Just remember that this is ORP, orientation reversing parameterization. All right, now let's get to the flux integral part. So the flux integral of the curl of f over the surface S will be equal to a double integral over the domain D. Oh, we parameterize this curve right here, so D is actually going to be back in this two-dimensional drawing. This triangular region 1 and 3. So when we do this integral, we'll probably treat this as a type 1 or type 2 region as a double integral and then go from there. However, when we take the dot product of the curl of f and r cross r, which is what we're going to do, dot product of the curl with r cross r, or rx cross ry, that is going to give us a double integral over this domain of the dot product. So that's 1 times 1, 1 times negative 1, and 1 times 1. So you see what happens here is that this is a constant. Not only is it a constant, but it's actually equal to 1. And if it was just a constant, we can just imagine taking that out. But no, it's a constant, 1, and so we know that this is the area of D, whatever D is equal to. Well, D is this domain, remember? So the area of a triangle is 1/2, the base is 3, and then the height is 1. And so that should be our result, 3/2. Oh, but remember that we had an ORP. And so in all this situation, when we did this parameterization, we need a negative sign in front. Negative sign, negative of the area. So our final answer should be -3/2. Okay. Just to show you a picture of the region that we're talking about, here are the points given by the directions, and if we were to do this directly, we would need to parameterize each of these curves, which is going to be line segments. And again, it's kind of hard to look at, but if we take a look at this from a two-dimensional point of view, this is the curve that we're looking at, or this is the region that we're looking at. Let's go back to 3D now and introduce our plane. Our plane is z is equal to 1 minus x minus y, and you can see that all those 3 points are on that plane, which is a good sign. Again, we only care about the region that we're trimming, so not the whole plane, but just that little region. And so we can hide that plane and take a look at the region that we're actually looking at. And it's going to be this region, which is a triangle. Okay. All right. Well, I think that's about it with the whole picture. And don't forget that your parameterization that we had for the plane is pointing up, but since the curve is going clockwise, we actually want the normal to be pointing down, so we had to acknowledge that our parameterization was going in the opposite way, hence the negative. All right, I hope that helps, and good luck.